This lecture is going to be mostly about the first law of thermodynamics, which is the conservation of energy. Now, energy is actually a pretty mysterious thing. Whatever it is, it goes from one form to the other form to a third form, but the total amount remains constant. Now, the first law of thermodynamics makes the essential statement that heat is a form of energy. And so energy and heat are freely interconvertible into each other. When we talk about actual thermodynamic systems, well, things can get pretty complicated. So on the one hand, you can have a system that is isolated from the universe, which exchanges no heat, no particles. Or you can have a closed system, which, yes, it allows heat to be exchanged with the environment, but not particles. But then you can also have an open system. An example of an open system is you and me. We are thermodynamic systems. We exchange heat with the environment. That's why I'm wearing this sweater. But also, when we breathe in particles or exhale particles, we're exchanging particles there with the environment. And so that's an open system. Of course, plants are that way. Engines are that way as well. But first, let's concentrate on the different forms of energy. Through this cartoon applet, let's see how energy can change its form from one to the other. Let's give some kinetic energy to the pedals, which then moves a generator. So mechanical energy is converted now into electrical energy. The electrical energy then gets converted into heat. But this mechanical energy going into electrical energy can also be converted into light energy. Or, of course, it could be converted back into mechanical energy. So, mechanical to electrical, back to mechanical. We could also see how the gravitational potential energy of water, when it falls, can turn this generator, resulting again in mechanical energy, or maybe used to heat water. And finally, let's look at the sun, which shines onto a photovoltaic array, which then generates electricity, which then is used to create heat or to produce mechanical energy. As in every branch of physics, we need units. The unit for heat generally used is calorie. 1 calorie raises the temperature of 1 gram of water by 1 degree centigrade. Now, of course, since heat is energy or work, therefore there is an equivalence between heat and the mechanical work that is done to produce it. So remember, heat is energy, energy is heat, and therefore obviously the dimensions of heat are the dimensions of energy, and that means mass into speed squared. And so energy is mass into distance squared over time squared. Let's now talk a little bit about internal energy. So take any system, the most general one. Maybe it's got a lot of subsystems inside. So maybe there's a box over here, another over here. Inside this box, there could be atoms and molecules, maybe molecules shaped in very bizarre ways so that they spin around, they move around, they interact with each other. Maybe the boxes interact with each other, whatever. The sum of all the energies is then the total internal energy of this system with all its subsystems, everything that moves inside and attracts or repels each other. Of course, this is very, very complicated. So the easiest thing is to look at a box like this maybe and fill it up with just a few atoms which are sufficiently far apart from each other so that they only very rarely interact with each other. Most of the time, they're too far apart from each other. And this is what we call the ideal gas. Here is an almost ideal gas. It's an empty box. Let me put in some atoms into this. I've already put in too many because you can see that they have started colliding with each other. However, in a few collisions, both with the wall and with each other, equilibrium is attained. Equilibrium now means that the distribution has become more uniform. There are almost as many in one corner as there are in another part of the box. Let's look at the pressure. So the pressure right now is 5.8 atmosphere. You can see that over here. Let's see what happens as we increase the temperature. So I'm going to heat it up. The temperature is going up and up and up. It's now 500 and something. Okay, so we'll stop it over here. You see that the pressure has gone up now. It's 12.2. So what we see over here is that the pressure is proportional to the temperature as measured in degrees K. We can do a lot of other things, and I hope you will play around with this. So let's, for example, decrease the volume. Let me go over here, let's say half that volume. And you can see that the pressure has almost doubled. So I halve the volume, the pressure doubles. What will happen if I make a small hole in this box over here? So let me open it up a bit, and you see that the molecules, the atoms, are beginning to leave. And slowly they will empty the whole box. The pressure will come down. So this is what happens when the tire of your car or motorcycle gets punctured. Now, of course, that animation is not a derivation, but you can understand that pressure increases as you increase the temperature. So this is what is called an empirical law, just as this is an empirical law that as you increase the volume, the pressure decreases. This is called Boyle's law. Now, if you put this and this together, you get PV is proportional to T, and then there is a constant here. Well, there's the number of atoms or molecules in the gas. R is a constant known as the gas constant. It has a value that you can find experimentally. You could write this as PV minus nRT equals 0. This is what is known as the ideal gas law. So in a gas where there are no collisions, you would have this relation holding. Now, of course, in a real gas, you always have collisions, and this equation keeps its form. So it's, look over here, this is a function over here of pressure, volume, and temperature. The most general equation of state for a gas, a liquid, or a solid is some function of P, V, and T equals 0. Determining the equation of state is not easy. It requires knowledge of what is inside the gas and how to solve a many-body problem. Let's now talk about the first law of thermodynamics for an isolated system. Isolated means that no particles, no heat, nothing is allowed to cross this dotted line over here. So it is completely cut off from the rest of the universe. Whatever its energy is internal. So U is the internal energy contained inside the system. Okay? That means that there cannot be any change of the internal energy of the system. du is equal to 0, and that's the first law of thermodynamics. It's just the conservation of energy. So, for example, here is a thermos, and it's not a perfectly isolated system, but it's a fairly good example of one. The coffee inside will remain hot. The internal energy U will remain constant. du is 0. Now let's talk about a closed system. A closed system means that no particles can enter or leave the system. However, you can put in heat. So let's imagine a small amount of heat dq being put into the system. You could, for example, put it on a fire, a stove, or in a microwave oven, whatever, and this would be a small addition, dq, which then increases the internal energy. And so, the first law of thermodynamics says that the internal energy of the system has increased by the amount of heat that you have put into it. Whatever you put in, the internal energy increases by that amount. Now, you can also do work on this system. So, as we shall see in several examples later, you can do work on the system. In this case, I'm doing just a small amount of work, dW. And now the conservation of energy says that the increase in the internal energy of the system, which we've called U, will be both the heat added and the work done. The sum of the two will be du. Now here, work has been done on the system, and in that case, this over here is a positive sign. However, you can take work from a system. In other words, this system can do work itself, in which case the work comes out of the system, and then if we draw it this way, du would be equal to dq minus dw. Equally, suppose that this system was to produce heat. Well, in that case, dq would be pointing outwards. Here's an example of an internal combustion engine. So, heat is put in, so whatever the fuel you burn gets converted into heat. That heat goes into this closed system, that is to say, no particles are entering the system, and out comes the work in the form of a force pushing the piston down. When the piston is pushed down, it can cause the crankshaft to move, and that then turns the wheels of the motorcycle or the car around. So what we have over here is an engine that converts heat into mechanical energy, into work. Let's calculate the increase in internal energy of any system. Well, this substance over here, it is a gas. I'm not saying it's a perfect gas, but it's some kind of a substance over here. So here's a pressure which acts on this piston. When this piston moves through a distance dx, that's a force that has moved a certain distance along the x-axis. Okay, so let's call the work done on the gas as dw. So we are putting in work into the system. The work done is the force, so the force that is being applied to the piston times the distance moved by the force. That's the usual definition. Now I'm just going to divide by the area of cross-section of this piston, and then I have to multiply it. But what is A dx? A dx is just the change in the volume. So the small amount of work that is done is equal to the pressure multiplied by the small change in volume. Now in this case, dq is equal to 0. That is to say, no heat is entering from outside, and so obviously the increase in the internal energy of this system, of this gas or this metal or whatever material is here, is going to equal the amount of work that has been put into it, and that we have just calculated is PdV. So du is equal to PdV. This is something that we are going to be using again and again. Finally, let me consider an open system. In an open system, you can have particles that enter or leave. So in this case, here is our system. As before, you can have heat coming in, and you can have work coming in, that is, you can do work on the system. But the difference between the closed system and the open system is that particles can be added or removed from the system. So if dn is pointing in, then obviously you are adding particles. If this arrow is pointing the other way, that means you're removing particles from the system. And here the first law of thermodynamics is as before, dq plus dw, but there's a new term. That new term is proportional to the number of particles that you have added in. Of course, I've written dn as an infinitesimal. Now you'll ask, can I really do that? After all, dn cannot be less than 1. I can, at the minimum, add one particle or remove one particle. You can't remove half a particle, but this is fine because the number of particles inside this is in the billions and trillions, 10 to the power 23 or whatever. This constant mu, which is in front of dn, will be different for different systems, and it is called the chemical potential of that particular system. Here is an example of an open system. So if you have a saucepan without a lid, see, if it had a lid, then it would be a closed system. But this doesn't have a lid, so you can put in sugar, coffee, tea, whatever into the water. And that will increase the internal energy of that system of water plus saucepan. Of course, the chemical potential will be different for sugar and different for coffee. So strictly speaking, we should have mu sugar, dn sugar, plus mu coffee, dn coffee. But that's obvious. The concept of exact differentials will be needed again and again in thermodynamics. And so let's be clear what that means. As you remember, in calculus, we talk of functions. A function is like a machine. You give it an input x, out comes a number f of x. So for example, x squared or sine x or e to the x or whatever, these are functions. If I take a function at x plus dx, subtract it from the function at x itself, call that difference df, then you know from calculus that this is just df by dx into dx. And there will be corrections, so there will be plus something that's proportional to dx squared, then dx cubed, etc. But when we take the limit when dx is very, very small, then this is all that remains. Now another way of writing this is df is equal to partial f by partial x. The partial derivative here and the ordinary derivative here mean exactly the same thing if there is only one variable. Okay, so here df is an exact differential because it is related to the difference of the function at two values of the input. However, there are quantities that are not exact differentials. So, for example, dq is not an exact differential. Suppose I was to add 1 calorie of heat to the system. Now, it could be done through a gas flame, burning wood, through a microwave oven, or whatever. In this case, dq would not be the difference of two functions. You could call it an inexact differential. Another example, work. So in the same sense as before, suppose I was to add 1 joule of work by raising this from here to here. I could have done this in 20 different ways, and so the small amount of work done in raising this object was not the difference of two functions. Again, the same moral, that dw is not an exact differential. You cannot say that this water contains heat. All you can say is it has internal energy. So if I add some heat over here and do also some work on the system, the increase in the internal energy of the system will be the sum of this and that. That will be the increase of the internal energy, and you can say that the system contains energy, but you cannot say it contains heat or it contains work. Actually, that makes a lot of sense because heat is not separate from work. The two are exactly the same. We often talk about thermodynamic variables. Actually, we have met several of them so far without calling them that. So thermodynamic variables include pressure, volume, temperature. We'll come to other examples later. So if you have a piston and there's a pressure on this, well, that's the pressure on the gas. Now, if we know all these variables, all these thermodynamic variables, pressure, volume, temperature, then we say that we know the state of the gas. It's important to realize that a thermodynamic variable is a system property. That is to say, it's a property of this particular system. It doesn't matter how you heated up the gas to temperature T. Thermodynamic variables, of course, can change. The temperature can change, the volume can change, the pressure can change. The change depends only on the initial and final states of the system. So, again, I remind you that the state of the system is defined by pressure, volume, temperature for this gas. And so, the pressure, if it goes from P1 to P2, the change in pressure will be P2 minus P1. The change in volume will be V2 minus V1, etc. Later in this course, we'll talk about other thermodynamic variables, which could be, in this case, the chemical potential, entropy, enthalpy, but we'll come to that later. All I want to say is that these are also thermodynamic variables needed to specify the state of a system. In the last slide, you saw what happens when we change one variable. In that case, I'd called it x. Now, what happens if we have changes in the other thermodynamic variables? So, suppose that f is a function of the variable x1, x2, x3, and we make small changes in each of them. So, x1 becomes x1 plus dx1, x2 becomes this plus dx2, x3 becomes this plus dx3. The difference is what we call df, as before. So this is equal to the partial derivative of f with respect to x1 times dx1, and the same for the others. In the first case, df by dx1 means that you hold x2 and x3 constant. Here, you hold x1 and x3 constant. In other words, you simply say that x1 and x3 have some fixed value. And finally, here, x1 and x2 are kept constant. So it's very simple actually. Imagine that there was only one variable, x1, then you would have only this term. If there was only the second variable, not the first, then you would have only this. If there was just variable x3 and none of these, then you would have only this. However, if you have all of them, then you simply add up the small changes. This is something that we will use again and again.